We want to make the best large language model in the world and have it fully open sourced and document and teach how we did it. And we want to make it better than closed source companies, and they will benefit too, so this is a friendly competition. This blog by Hugging Face is really good at explaining how you scale your LLM from one GPU to multiple GPUs, so let's understand it. This diagram shows how much memory each different LLM configuration takes. So we have preset Llama 8B. We see that activation memory is 140 gigabytes, where each of the layers take 4.38 gigabytes in memory, and there is in total 32 layers, which we can see here, number of layers 32. And then within each layer, we have attention 1.94 gigabytes and feed forward 2.19 gigabytes. We have hidden dimension, for example, so if I increase hidden dimension, let's say 5, then we see that more parameters gradients get more of memory. Now there is 300 gigabytes. So we see both proportion and total here. And then Llama 3405B, there is a big difference. A lot of parameters go here, a lot of memory goes here. Parameters, gradients, optimizer, averages. Don't worry if any of this doesn't make any sense, because this is why we have this tutorial. They also made this tool that lets you predict memory. How you actually scale your LLM training depends on your infrastructure, such as the kind of chips used, interconnect, etc. We will need to benchmark and test several setups to figure out which one is best. They ran more than 16,000 experiments to test different distributed training layouts and model sizes. There are 3 key challenges. Memory usage. This is hard limitation. Model needs to fit into memory, otherwise we cannot do anything. Train. Compute efficiency. We want our hardware to spend most time computing, so we need to reduce time spent on data transfers or waiting for other GPUs to perform work. Communication overhead. We want to minimize communication overhead as it keeps GPUs idle. To achieve this, we will try to make the best use of intra-node fast and inter-node slower bandwidths, and to overlap communication with compute as much as possible. Sending data and computing data should happen at the same time, and compute shouldn't wait for data to arrive. In many cases, we can trade computation, communication, memory, and finding the right balance is the key to scaling and efficient training. So small batch size versus large batch size. Batch size is how many examples you train at once. So if you train on small batch size, then you get fast updates. Early in the training, that's very useful because model doesn't know anything, so it learns quickly. You update. A large batch size, model needs to wait more and then gets a lot fewer updates, so it learns slower because every update is gonna help every other update after it as well. So it kind of compounds. As the model becomes better, it makes better decisions and becomes even better faster. So small batches are gonna make it better a lot faster in the beginning. The issue is a big batch will average a lot of tokens, so it's gonna find good average direction to go to. Small batches are gonna be more noisy. They're not gonna average so many tokens, so they're gonna move a bit random directions. Larger batches, like asking hundreds of people before deciding, you'll get a very stable and accurate picture of what's best, but it takes longer to gather opinions before you act. This is also a problem in the beginning, where, as I said, if model gets better, it will make better decisions, and then it will compound the improvement on itself. So we need a lot of fast updates in the beginning. So smaller batches. It doesn't make sense to have a huge large batch in the beginning where model even doesn't know what to do with the tokens. So small fast improvements are better. Then small batch, since you average less tokens, each token contributes more. And large batch, you average more tokens. There is less noise, but also every token contributes less on average. So small batch is better in the beginning to explore and learn quickly, and large batch is better later to stabilize and converge, and to reduce noise, random noise of small batches. Batch size also affects the time it takes to train on a given text dataset. A small batch size will require more optimizer steps to train on the same amount of samples. But you can change a batch size around the optimal batch size quite a bit and model will train well. So model is not so sensitive on the batch size if you keep it around optimal batch size. You can actually change it quite a bit. So you can measure batch size in batch size number of tokens and batch size number of samples. So number of samples times sequence length is gonna give you a number of tokens. Sample is just a sequence, one conversation, one full sequence length. A sweet spot for recent LLM training is typically in order of 4 to 60 million tokens per batch. This is absolutely huge. It looks so huge. 60 million tokens per batch. Batch size and training corpus size have been steadily increasing over the years. Llama 1 was trained with a batch size of 4 million tokens and 1.4 trillion tokens in total, while DeepSeek on 60 million tokens in batch and 14 trillion tokens in total. And here we run into our first issue out of memory. Issue if GPU doesn't have enough memory to hold our full batch of 60 million tokens plus models and stuff. So when we train, we store model weights, model gradients, optimizer states, activations needed to compute the gradients into the GPU. One note, there are other things that also want memory, like CUDA kernels that typically want 1 to 2 gigabytes of memory. You can compute that or try that by running these commands in this blog. I'll leave this URL below. And some other things take a bit of memory, like buffers, intermediate results, and some memory can't be used due to fragmentation, but it's only a bit of memory. These items are stored as tensors in memory, which come in different shapes and precisions. The shapes are determined by hyperparameters such as batch size, sequence length, model hidden dimension, attention heads, vocabulary size, and potential model sharding, as we'll see later. Also, each of these can be in different precisions, FP32, BF16, and FP4, which require 4, 2, and Y bytes to store respectively. You can use mixed precision training, so you use higher precision where necessary, like for result accumulations, and lower precisions for storing weights into memory, for example, whereas high precision is not necessary. We'll see about that later. We need to also discover which setup works for our LLM. And we also need to discover how we can use FP4, the newest one. One good way to measure how much memory your LLM needs is just to load it into GPU and see. So there is this PyTorch profiler. We can understand how memory is allocated throughout training with it. We can see that memory utilization is not a static thing, but varies widely during training and during a training step. Here we see that this looks very different from these three. We also have these spikes here, so let's see what all of this means. First, the activations increase quickly as we do the forward pass. Then during the backward pass, the gradients build up, and as the backward pass propagates, the stored activations used to compute the gradients are progressively cleared. Finally, we perform optimization, during which we need all the gradients, and then update the optimizer states before we start the next forward pass. We will learn more about this profiler, which I also need to learn more about, but let's see how much memory different models need. Here we can see as soon as we reach 7 billion parameters, then we cannot fit our model into the big GPUs like even H100, so they have too much. Now I plan our LLM to be just 3 billion parameters initially, so that's gonna be okay. Activations are the intermediate outputs produced by each layer of a neural network when you pass data through it, a forward pass. So input, layer, activation, next layer, activation, etc., then output. Here, activation age is the output of the first layer, Y is activation for the second layer. So you can look at that as like the neuron. So age is the neuron value, and then Y is the neuron value on this second layer. X is the input, then this neuron, then this neuron. And you see how its sequence length, activation memory in GPU grows exponentially. Gradient accumulation is a trick to simulate big batch size while not having the memory. So you split big batch into small micro batches, perform forward and backward on each micro batch, you accumulate the gradients, add them up, and then perform optimization with those added up gradients in the end. In practice, the optimization step is conducted not on the sum but on average of the gradients, so that the result is independent of the number of gradient accumulation steps. So it doesn't matter on how many mini micro batches you divide the whole batch. You just take the average of small batches. So this is the model. We do forward, backward, forward, backward, forward, backward, and we find average of all of the backward of all the gradients, and then optimization and update model. But the issue is you need to do multiple forward and backward passes, and if you did it all at once with big batch size, then you would not need more computation like this. But these forward and backward passes are independent from each other, so they can run in parallel, so we can put them onto different GPUs. So the best tool to measure this communication between GPUs is Profiler, and this will be extremely useful to measure bottlenecks especially, and what's making our setup slow. This is code example. It's gonna generate some traces that we can check. This trace helps you identify bottlenecks like sequential compute and communication that could be overlapped, idle GPU time waiting for data transfers, CUDA synchronizations and memory movement between GPU and CPU, kernel launch overhead on the GPU. We will learn more about PyTorch Profiler in a different video where we're gonna do some experiments with it. And then we go to the data parallelism, where you copy the model onto multiple GPUs and then run small micro batches on each GPU and then add up gradients. I just explained that in our gradient accumulation steps part. So we will average all gradients in a batch using an operation called all reduce. So there is a naive way to implement data parallelism, and it's after the backward pass computation, we wait for the gradients to synchronize, communicate of all of the GPUs before we calculate averages and stuff. Could we overlap this communication with our computation? Yes. This can be achieved in PyTorch by attaching an all-reduce hook function to each parameter. You see, as the backward pass is happening, it's already sending data to be calculated, accumulated and stuff. There are two more methods, but let's see which one we use. We're gonna learn more about that one. This blog post is absolutely ginormous. It's actually so valuable, so good. But we're not gonna read it all at once. I'm just gonna start coding my multi-GPU setup now, I guess, and then explain what I actually use. We're gonna need a year to master this blog post, and it's so valuable. I hope we can also produce some things like this on our YouTube in our community. Check out other videos on my channel and see you next time.